Yeah. Okay, well, let's first, actually what we should do is look at the schedule because it changed a little bit. Okay, so in order to give you a bit more time to get prepared for the presentation of your proposed project, I moved that back. And where did we move it to? Okay, we moved it to that proposal presentation will be May 15th. So that's like 2 weeks, okay, from now. And ideally, you guys get to me who your partners are. I have one team already that wants 3 people, so that's done. We're good there. And then everybody else can find a partner. And if we can get that done by, say, Wednesday, just 2 days from now, would be terrific. I sent out a list of people who are in the class. It was names. I'm assuming you can find their email if you have their name. Is that, yeah? Okay. So, and then if you just send me who you want to be partners with, we'll make a little chart, and that'll be that. In order to do this, we're going to shift some of the lectures. Okay, so today we'll do PET scanning. And then Wednesday, we'll go right into CT as opposed to the original schedule. For whatever reason, I put it on May 3rd. We'll start CT, okay? And then everything will just shift up until we do this one class where we have the discussion about various proposals. It would be great if this was like an open discussion and people presented an idea for a project. You know, this can be 3 slides. Just what is the background of the topic that you're addressing? Is there an outstanding problem, or is it something that you know, you basically just want to clarify to yourself, like what the technology is, and then the approach, and you know what the output will be. Will it be essentially a in-depth research kind of review where you review, say, 10 of the top papers in that area, and you distill it down to something that anybody can carry away on a couple of slides, which itself is a fairly major undertaking. Or it can be a simulation that you just create your own data or get data from a public source, or you can come to me and ask for specific data that you need for a simulation, and we can try and get that done. In the lab, we have a fairly large database of CT scans. That's about it. We don't have a big database of MR. We have like a small database of MR. However, MR data is available through online through a lot of these competitions and things like that. So normally you can get that stuff online. CT is harder. There aren't as many online databases with full CT data, specifically cardiac CT. So in that case, we could create a data set for your project. And so we would hyper de-identify the data, probably turn it into nifty files or something like that. And then you could use that data to run whatever simulation or algorithm you want to develop. I welcome you to extend your thesis project or your research direction that you're undertaking as a graduate student. You're welcome to map that to some problem in medical, cardiac medical imaging, and push it farther because I think it would be intrinsically more interesting for you probably. So that's always fun when that happens, when they're doing some sophisticated thing in signal processing, whatever, and they map it straight onto this problem. That's actually really beneficial for all. So that would be terrific. Are there any other questions about the timing or the nature of the project or anything like that? Okay, terrific. So today, those of you who took 280B last year, this will be review because it's positron emission tomography physics, you know, and so that hasn't changed in a year, so it's going to be kind of review. Whereas if you go into the applications of artificial intelligence to cardiology, that changes every 3 months, right? That is a field that is just moving very, very quickly and producing some pretty exceptional results. So that's the new schedule. I've edited the calendar here with the course summary that has the new timing of the lectures. I will go back and edit this description part today, probably. And I'll put the lecture slides for today. And I think the Bushberg chapter is already in the files folder for this lecture. So the, additional reading. So if what I'm saying doesn't make sense, you can go to that reading. Okay, so let's get started on PET. PET is a really cool technology. It's been around a long time. So I'm going to get rid of this first. And there we go. So here's the associated reading for these slides that for most of the slides you're going to see today. So it's like any, scanner that we use to image the heart. The patient's usually on a table, and in this case, it's a cylindrical format. The detectors surround the patient from all directions, unlike SPECT, where it's usually a detector that's flat and in one direction. In PET, it's almost always a cylindrical geometry of the detectors. And in most cases nowadays, in order to get the attenuation correction spot on, there's also a CT scanner incorporated into this cylinder. And that CT scanner is nowadays, normally a really good CT scanner. It's, 64 slice CT scanner. And so a helical acquisition of the patient is done such that you can do really accurate attenuation correction, which, as we'll see in PET, is not as important as it is in SPECT. However, still improves the estimates in the images. So I would say that we'll see what the limitations are in PET resolution, but as we move forward. PET, or the development of PET, has not been driven by cardiology. Okay, it's been driven by cancer. And the reason is PET, when you're detecting, it's the same principle as SPECT, where you inject what's called a radionuclide or something that's radioactive into the patient, and then the patient glows. But the thing about PET is you can detect very small amounts of this radionuclide in PET. It's very sensitive. So if you're seeking out very small metastatic lesions, right, and you want to know, because it's a real binary sort of transition for a patient as to whether or not the tumor has broken off and has metastasis or not. And you can see tiny little lesions with PET. For cardiology, we're interested in things sort of on the order of a sugar cube. If you're looking at perfusion, it's like a chunk of tissue that big. So the resolution doesn't have to be spectacular. It sure looks better when you're looking at the picture, as to whether or not things are functioning. But if what you're interested in is, say, perfusion of the myocardium, which PET is often used for, or viability of the myocardium, are the cells alive at all, superspatial resolution isn't as important. However, as we'll see with one of the clinical examples here, with PET, you could actually detect inflammation of the arterial wall. So if you have a lot of, white blood cells and things going to a piece of damaged tissue, it gets inflamed. Actually, its temperature goes up a bit, the tissue, it swells, and you get this hyperactive metabolism there. And PET actually is able to detect that. So you can imagine that pre-coronary disease, like, so you haven't had a heart attack yet, you haven't had a thrombus or anything, but the vessel itself is just inflamed. That can be detected on PET. And so that's really early detection of cardiovascular disease, such that who knows whether it's going to predict you're going to have a heart attack or whatever, but it can tell you whether or not you're susceptible to disease. The other thing that it can do, which a lot of, we'll see how CT and MR can also look at viable versus infarcted myocardium. But PET can actually do this metabolically. So even if the tissue isn't contracting normally, but it is still alive, PET can tell you that tissue is still alive, right? And so therefore, and it's one of the holy grails of cardiology is, should I revascularize this patient in order to revascularize this chunk of tissue in their heart to save it, to salvage that tissue? If somebody has a heart attack and they show up at the ER and you get the vessel open in like 45 minutes, normally the tissue downstream lives, it survives, right? And so now you've still got totally viable heart everywhere. If, on the other hand, they have chest pain, they wait 2 days, they get to the hospital, oftentimes the tissue distal to that lesion has died, and it becomes a scar or an infarct. And so determining where you are in that progression of events is something that people have been trying to do for a long time. And PET has been touted as one of the answers for that. And we'll see how in a minute. So this is one of the cool things about this technology is it's, the physics is just really cool. So you there's a number of atoms that are unstable in the sense that they will decay by producing actually a positron, and the proton itself turns into a neutron. Okay, and so you convert a proton into a positron and a neutron, right? So there's a lot of positrons observed in the world, but there's countably infinite more electrons in the universe. Don't know why that is. Why in the early genesis of the universe, this balance of positrons and electrons, when they all sort of basically annihilated each other, and there's just a bunch of electrons left over. It's like a residual, right? Anyway, a positron and electron, when they meet, when they collide, they turn into photons, right? So both particles disappear, right? And what is left in their stead are two photons with equivalent energy in terms of E equals mc squared energy, right? The photon, its energy is proportional, obviously, to its frequency, right? Or its wavelength. And they're half an MeV photons. They're 511 keV. And there's two of them to conserve momentum, right? So if the positron is just floating around in the tissue, it's been ejected from a nucleus, right? And so in this case, this example, the fluorine 18 becomes oxygen 18. So the positron comes out of the nucleus, and it's ejected with a certain amount of energy. And so it wanders around in the tissue, and finally, its kinetic energy gets low enough that the cross-sectional probability of it meeting an electron and then annihilating is high enough when that happens. And, and then this momentum, the total momentum of both of these particles is pretty close to zero. And so you get photons coming off with zero net momentum, basically. there's a little bit of uncertainty in the fact that they're usually 180 degrees apart, plus or minus, here it says 0.3 degrees. So there's some kind of distribution, of that. But now, what do we have? We have a photon. It's not an X-ray anymore, right? It's a gamma ray, and it's coming out with this kind of energy. Remember, our top energy of X-rays that we use is about 140 keV, something like that, and this is 511 keV. So it's a very high energy photon. And because it's high energy, it'll shoot through tissue, right, a long way. It doesn't get absorbed that easily. So you have this photon going this way, this photon going this way, which is really powerful in terms of encoding where that photon originated from, right? The fact that you have both of these photons coming off in essentially a straight line. And this is why it is fundamentally different than single photon emission tomography. So here's the detector ring around the patient, and we have this positron is created by this decay inside the patient. It diffuses in the tissue and then hits an electron, and the two 511 keV photons come out in opposite directions. The fantastic thing about this is you can then detect, you have an array of detectors, and so you detect that you have a 511 keV photon here, and you look at your history of detectors around here and you say, was there a coincidence detection when this thing hit? And you look down here and say, yes, there was. It's right here. It was within a nanosecond or something, that there was another detection here. And so you call this, a coincident event, and you just record it, as something that goes in your list of coincident events. Okay. What you do know at this point is that event occurred somewhere along this straight line between these two detectors. That's the information that you have in hand at that point. You don't actually know where along that line inside the patient it occurred, right? But you do know it's somewhere along that line. And this is very similar to SPECT or CT, right? Where we look along a line in the patient and we integrate what happens along that line. Same with this. So you can see that there's a couple of things that can go wrong. One of them is if the activity was too high, does your physics and electronics of the detector get saturated? So you just get too much activity. You can't differentiate. You can't make coincidence detection because there's just too many things happening at once. And so you want electronics that are fast enough for that. But in these days of, the Large Hadron Collider producing a splash of particles, like billions of particles, and then, tracking these traces and things like that, we should be able to get that done, right? Which is interesting in its own right. But so if this is the detector, so the patient, let's put the patient on a table here. So let's say the patient's head's here, their body's here, and their legs are down here. And they're going to slide along this way. That's not to scale. You can run this in two-dimensional mode, right? Where just like in nuclear medicine, we put these sepia or a anti-scatter grid in this one dimension in order to keep our detection of a slice isolated. And so now we truly have two-dimensional data, right? And that makes the math easier. It makes the reconstruction easier, right? Because you have this two-dimensional set of projections.
Found this on the web.
Well, thank you. I don't know how, I still haven't figured out how that happens. I don't know if anybody knows how that happens. This is the problem about being old and having new technology. Okay. A more efficient way of doing this is to just bite the bullet and say, we're going to acquire three-dimensional data, truly three-dimensional data. And don't put these anti-scatter grids here, just have an open detector and then have the coincidence in 3D, right? So now it's your reconstruction for a specific slice is not going to be as simple, right, as it was for the one where the data is all contained inside a two-dimensional structure. However, that data can be used to reconstruct a 3D volume in a more generalized inversion than just what we saw with the convolution back projection algorithm in CT and SPECT. So here's, so this is called the line of response, or the LOR. Here's our patient. We have a positron emitted. It annihilates here. And then we detect an event here. We detect an event here. They are within a certain time window. So we say they are coincident. And then this defines a line of response here, right, along there. Of course, photons interact with matter. And so a photon can proceed away from our original annihilation point and then essentially scatter off a nucleus or an electron or something like that and come and move up to this detector and cause an event or a flash here, whereas this 511 Ke photon comes here. So these will be coincident, right? And you will get the wrong line of response for that. It'll say, well, that must have occurred somewhere along here, and that's obviously wrong. And the one way of minimizing or dropping the number of these incorrect lines of response from scatter is tighten up your energy width, because we know that when this scatters and it lands here on the detector, it has a lower energy than 511 keV. It didn't pick up any energy in that scatter. It left some energy behind, right? So the higher the angle of scatter, the bigger the energy change in that photon, and you will have the ability to just eliminate this coincident event by saying, well, one of them scattered. And then you can have true overlap of events if you have enough activity going on. This is all relative to the electronic width of your detection window. How tight can that window be? If I have an event here, fires off, and I have an event here and fires off, so I get a coincidence here and here, and that gives me an incorrect line of response for that. And this is the saturation of the activity. And so, that PET has with this energy elimination or filtering, it sort of has a natural anti-scatter method built in, right? But it still can cause some background activation. One of the things you can also do, I don't know if I have a slide on this. Yeah, I think we talked about it here. But you can imagine that if you just make your electronics better and better and better, right, such that your coincidence can go down to picoseconds, right, that you can call this event and this event coincident and measure the time difference between when this occurred, because it's a shorter distance, to when this occurred. And then that would give you an estimate of how far along this line that event occurred, right? And so that actually can be done on a modern scanner. Very similar to SPECT in terms of how do you detect a 511 keV photon. You need a fairly sensitive or thick chunk of detector in order to have a cross-section that 511 keV photon will interact with your detector and cause a flash of light. And that's how it's done. Many materials for these detectors have been used and attempted, right? And, you know, the ideal material obviously would catch every photon at 511 keV, ignore photons that were at a lower or higher energy, which is virtually impossible to do. But that's what you would like. And you would like the flash to be very bright for a very short period of time. And so normally what these flashes look like, they get bright very quickly, and then they have an exponential decay in terms of visible photons that come out of this material, right? And they're on the, you know, this is a classic material, and it's on the order of 12 nanosecond decay, exponential decay of brightness of that flash. So, you know, people have been using different mixtures in these crystals to try and make a light flash, which is shorter. And this LSO detector seems to get 4.5 nanoseconds, right? So that gives you an idea of the temporal resolution of the detection itself. So what the maximum rate of photons hitting this detector can be before they start overlapping. And it could also, if you wanted to just figure out, say this is a meter, right? And you've got a 4.5 nanosecond window on your decay curve. Let's say, what is the resolution along here if you wanted to measure a time difference between these two events, between this one, right, over here and this one? This one's going to be a little bit later than this one. So as that comes together, let's just say it's 4.5 nanosecond resolution or 2 nanosecond. What is the distance that you can measure there? And, you know, remember, this thing is traveling at the speed of light, right? So it's 3 times 10 to the 10th centimeters per second or something. Okay. Oh, forgot this back end part. So the crystal, when it's made, they put a structure of the crystal such that when there's a flash, the light doesn't go uniformly throughout all of the crystal. It bounces off the walls of a column and then goes down into the photomultiplier tube here. Okay, so that helps, you know, keep all of these guys going into this one photomultiplier tube. And otherwise, very similar to what we saw in SPECT, right? In how you amplify up the signal to get a positive event. Also, if we go back to SPECT, where we had this detector and we had a scatter grid such that it was collecting data for some time along these parallel pathways. So we were, remember, building up a projection of the activity when viewed from a certain angle, right? So these were integrals through the patient. All of the activity along this line hits this part of the detector. And so you just integrate that up, how many events you're going to get until you get a reasonable signal to noise, and then you move to a new view. And you physically move the detector. In SPECT, the detector is fixed. It just sits in the same location all the time. Makes it a little more expensive because you have to have a lot more of these things. And then all of these events, all of these projections are happening simultaneously. Or let's say sequentially, but rapidly, right? So you want your rate such that you get these sequential events rapidly sampled. And then you have a large list of these events, right? And so we say, well, what about the coincidence of this detector and this detector? And that gives you a projection through the sample this way. What about the coincidence events between this detector and this detector? That gives you that sample. And so after the fact, you rearrange your sampled coincidence detections into these projections, right? And as you can imagine, if we're building these things up over time, you're very susceptible to any kind of motion, right? So if the patient's breathing, then basically these projections are going to change their shape and morphology as the patient breathes, and organs move up and down, etc. So I would say that's one of the chief resolution limitations of PET in reality, is the fact that heart's beating and the patient's breathing. What we did was, early on in the development of a hybrid machine called a PET MR scanner. And so now you can actually, if you have $5 million, you can buy a one scanner that is both an MR scanner and a PET scanner. And what we did was we continuously acquired low resolution 3D MR data while the patient's breathing, right? And then you create maps of where points in the patient go over time. And then you look at your list data and you remap those lists to different locations depending on that motion field. And you can improve the image blur from motion considerably, because the motion of breathing is fairly considerable, right? I mean, when you watch a movie of somebody in the essentially the transverse plane, that not the transverse, but the plane didn't come to my head, or say the sagittal plane. If you watch that movie and you see them breathe, their heart moves up and down with breathing about 2 centimeters, something like that. It's the excursion of the heart. And so that's it's a lot of motion if you're going to average that over time. It's a lot of blurring. So you can take this data, each one of these things, and say, well, at which phase of the breathing cycle did that occur? I will move it by 1.3 centimeters in my final reconstruction. And it worked pretty well. If you have continuous images of where the patient is, that obviously works best. If you count on a model of where things are as a function of breathing, it doesn't work as well. I mean, you basically reproduce the position of the heart from one breath to the next, sort of plus or minus 3 to 5 millimeters, something like that. So somebody will take a breath, heart comes back to the same position, next breath comes back plus or minus a couple of millimeters, right? The other thing is that depending on the rhythm of the heart, if the patient is in some kind of arrhythmia, their heart from beat to beat changes its morphology. If there's a long delay between any two beats, the heart will tend to fill with more blood before the beat. So then you get a one beat that has a really high filling, and then it goes down, and then there'll be a short beat, and so that beat is low filling. You know, it starts with a lower amount of blood, and the whole thing really is not reproducible anymore with respect to the QRS, or the breathing cycle. So there are fundamental limits, and I tried for years to crack those limits by measuring in real time what was happening. And I would say we never got an MR image with better than 3 millimeter full width half max, something like that, right? Even if we image for half an hour, right? So, so I think that's sort of the fundamental limit, is the reproducibility of the heart position with breathing and the cardiac cycle. So, here's another example of scattered photons causing, an error in the 3D line of activity. This one is a correct signal. This one, you could have a single event and wasted radiation in a sense, because it just exits the scanner. But it's much, I think, is more efficient, for example, in SPECT, in the sense that you have all these detectors all the way around the patient. ideally the patient would be in a sphere, right? So any photon that came out would get detected, but hard to organize that. So if you took a modern day PET scanner and then took a 0.5 millimeter diameter, vitamin B cap, just full of agent that was giving off a lot of positrons. You stick that in the scanner. The image that comes out is a Gaussian with about a 5 millimeter full width half max. That's how it goes. So regardless of how many voxels they put in the image or whatever, this is the fundamental resolution. It's about this, which for cardiology is pretty good, right? I mean, for myocardial imaging, that's great. So a 5 millimeter cube, it's like 1/8 of a sugar cube or something. It's a pretty small piece of tissue. If you want to look at a coronary artery or a coronary artery wall, then this is challenging, for that resolution. However, if what it is you're interested in is inside this whole coronary artery at this location, do I have upregulated basically inflammation, right? And then it would glow brighter. And so you don't really need super resolution. You just need to know whether at that location in the coronary artery, do I have inflammation? And so people have shown successful coronary inflammation maps with PET. It's pretty new. It's pretty exciting area of research. And if you wanted to look at that as a project, that would be cool. You'd have like about 4 state-of-the-art papers, like they were fairly recent. And like anything like this, where people push new imaging modalities into a new area, there's half the people don't believe it. So you're in a good space to investigate when half the people say it's crap, right? And it's actually pushing some kind of boundary that is probably worth breaking. And so that's a more fun space to be in than where you're just sort of figuring things out that are going to be true. So 3 things listed here that obviously change spatial resolution. One is if you have more detectors, right, your angular resolution is better for this coincidence detection. However, if you have more detectors, in order to get the same signal to noise per detector, right, in terms of sampling the photons, you need more dose, right? So you're going to have to ramp up the dose in order to keep the signal to noise per detector the same. You can always integrate the detectors afterwards, though. If you get all this detection done, you look at the signal to noise on one detector, and the bad signal to noise sort of is down around the 10s to 20 photons detected, right? And you're saying, well, that's not enough. This is going to be a real mess. You can take a smooth picture of all of those detectors, and you haven't lost anything by doing that, right? You just integrate, say, every other detector, or put pairs of detectors and average them. That is as efficient as it would have been had those detectors been twice as wide. That in photon counting, that's how that works, right? Which is good. That's not true of all imaging techniques, right? When you cut your detectors in half, sometimes you intrinsically lose the ability to re-average, not in photon counting. So the distances traveled by the positron before annihilation is like a fundamental physics limit that Lord knows how we would change that. Maybe you could, I don't know. But the positron comes out of the nucleus with a certain amount of energy, and then it has to lose energy in order for the cross-section for this annihilation to occur. And so it bounces around in the tissue. And that's usually around 2 to 3 millimeters, right? So if when you look at your 5 millimeter full width half max, part of that is the fact that even if you had a perfectly, a bazillion detectors around this thing. The glow itself from this source of positrons is going to be a Gaussian that has a 2.5 millimeter full width half max, right? It's not a little dot. And then the angular error, that 0.3 degrees, also adds to the sort of blur on the picture. In order to get a good efficiency at detecting these gamma rays, the 511 keV gamma ray, the detector itself, the crystal material, has to be thick enough that, say, you get a 75% capture or 90% capture of those photons. If it was really thin, right, most of the photons go through, you'd capture some. But the thicker it gets, the higher the probability gets that every photon will get captured, which is good. However, it gives you a problem in the sense that for those crystals that are not directly opposite each other, the width of material from which an event can occur is broader. And because of the depth of the crystal, if something's occurring between these two lines and hits this crystal and hits this crystal, right, you have an uncertainty as to what strip that was in. You just know it was in this strip, but you don't. So that also adds to the blur. So ideally, you want these really highly efficient crystals that you can make pretty flat, right? So here's some of the elements that will emit positrons. Sorry. So who knows, like, if you have a proton, an isolated proton, right, and you just put it in space, just like, leave it there. Do you know how long it would last before it decayed into a positron and a neutron? It's like forever, right? It's trillions of years, right? It just won't do it. And that's because the neutron actually has more energy than the proton. So it has to be in an area that's getting hit with something, or there's some kind of event occurring where you're injecting energy and causing that proton to make this transition. A neutron, on the other hand, this I didn't know until recently. If you take a neutron, you put it in space. You say, oh, okay, let's see, how stable is a neutron? How long would it last just on its own? It lasts 11 minutes is its half-life, right? Which is kind of cool. I did not realize that. Just like, why are there so many neutrons around that? And it's because when you bind them into a nucleus, like into helium and stuff, then they last forever, right? But an isolated neutron on its own just does not last. Anyway, so these are, the big hits in this field in terms of atoms that have been used to create as positron sources, right? And normally you have to make these in a small particle accelerator, which is a little bit of a what do I say, activation energy to get your PET center working, right? It's like, oh yeah, but you've got to have a place for the particle accelerator, right? And so you bombard certain atoms, right, with, I forget what the beam is. Is it a proton beam or electron beam, something? And it causes a transition, nuclear transition, that you then harvest, and you have these elements that are positron emitters. And I think I have a picture. Where's my, how do I get out of here? I thought I had a picture of I guess it's not here. Maybe it was in the introduction slide of a particle accelerator in a hospital. But anyway, okay, we're here. Okay. It's not a small object. It would take this room, basically, and it takes a physicist, has to be a full-time physicist is employed. And when you're going to have a study, you need to make the contrast agent on site right before the study. And the reason is these things don't last long. So carbon-11 has a half-life of 20 minutes, nitrogen-13, 10 minutes, oxygen, 2 minutes. So this one, you got to be booking, right? Because you're losing half of it every 2 minutes, right? Fluorine 18, which we'll see is one of the most common things used now in this fluorodeoxyglucose condition. It lasts 110 minutes, which is, you can do some chemistry, right? You can actually put it on things, do this and do that, and then stick it in the patient. And so this is the energy of the positron as it comes out, right? And then this is how they do maximal range. I don't know how this computation is done, but so this is like a sphere within which you are 99% sure that positron from your source, it's not going to cross the boundaries of the sphere. As you can see, it's not insignificant, right? They go pretty far in tissue. They can get all the way out 5 millimeters and stuff, but it's basically a Gaussian. Well, this is an interesting thing about the physics of this event in terms of correction for the attenuation of 511 keV photons in the patient. Because it's coincident detection, the attenuation correction has a different nature, right? And you can imagine if I have an event here, well, let's say I have an event over here. The probability that my photon will get absorbed as I pass through the tissue from here to here is fairly low, right? And the probability that it will get absorbed along this way along the path is much higher, that probability. As I move that position along this line, the joint probability of those two events remains equal. So that means that regardless of where the event occurs along the line, the probability of losing one to attenuation is constant. And that's kind of neat, right? That it has this self-normalizing behavior, whereas single photon obviously does not. It's just the probability is just dependent on your depth and the direction that the photon's coming out. However, there is, you still take a CT and you still do an attenuation correction. Okay. What's it say here? 20 soft tissue. Chance of both photons escaping without an interaction is about 15%. So obviously, because you have a coincident event, the probability of one of them getting absorbed is pretty high. And so attenuation is a significant issue. Okay. So let's look at SPECT and PET. Recall, this is done upwards of more than 10 million times a year in the United States, maybe 10 to 20 million times a year. This SPECT test is done for cardiovascular disease. This is much, much lower. It's mostly in high-end centers, high-end academic centers that have access to people and facilities that you could, you're going to install a $5 million PET center, right? And you're not going to do that in a private clinic. Like a SPECT scanner you can get from a manufacturer for under $1 million, maybe 500. Not only that, the manufacturer is perfectly willing to give it to you and take payments, right? So normally the way this is done is a manufacturer comes and says, oh yeah, we'll just put it in and here's the payment schedule, right? For this thing. And it just pays for itself in about 2 years or 18 months or something like that. So there was a time when I was in my late 20s, early 30s, where the centers were being opened just like hotcakes, these freestanding imaging centers. And they were being opened by physician groups who needed imaging data. right? And they weren't being able to get it at their local radiology or whatever. And the manufacturers and those private groups kind of got together, and the manufacturers were the financiers of these centers, and they just popped up all over the place, and they were extraordinarily profitable, right? And so a lot of people got very wealthy very quickly, and then state governments went, what's going on here? These people are getting so wealthy, and then they put rules in place such that physician groups could not build a center that they would send patients to, right? Kind of makes sense, like just from a feedback standpoint, that positive feedback could ramp up pretty quickly, right? Everybody needs a SPECT scan all of a sudden, right? However, cardiology kind of got under the radar there, and they still had their SPECT machine and their echo machines in their office, right? So as opposed to these freestanding clinics. But anyway, to get to a PET scanner, normally you have to be at a place like this or UCLA or Hopkins or something, and then you'll have the ability to get cardiac PET. Cardiac PET is not a common thing. So in reconstruction, you can do back projection on either one of these techniques, but both techniques now, because of the fewer number of events that you're using to make a reconstruction than, say, CT, they both use iterative methods for reconstruction. And that means you can do a back projection as your first estimate of what's there. You then take that first estimate and use it as an injection of a model that would create data, right? And then your model creates this data, and you look at the difference between what you've created and the actual raw data, right? And then you iterate on that until that difference becomes minimized with a residual that is the appropriate noise model, as opposed to artifact and things like that. And so those techniques grew actually in PET before anything else, because it was starved for protons or for photon detection events. And so they've been doing it for 25 years or something like that. And then these iterative methods got mapped into CT when CT had to turn down the number of photons to avoid high dose imaging. And so then CT started using these iterative methods for reconstruction about 10 years ago. And then the doses in CT remarkably dropped by a factor of 8, something like that, 7, 8, just by engineers saying, oh, well, we can use these iterative methods to recover image quality, out of this noisy data. And, it's you have to wonder, like, were they just lazy before that they, used all these photons? The easy way to make a great picture is use a lot more photons, right? So, so here we talked about this to a certain extent, in the spatial resolution in one of these gamma cameras or SPECT cameras, and roughly 10 millimeter full width half max, something like that. If you have something in a 30 centimeter orbit, and here it's about 5. Okay, so it's much better, and we'll see the pictures are much better. Here, the attenuation of the photons is greater, as we saw on that slide, so that only 15% actually get out as a coincident detection. So that's why X-ray CT scanner is included in these machines. So here, this is the CT from a PET CT scanner, showing you, a reasonably good CT image. And that the great thing about this is that CT is used in SPECT as well, right? The front end of a SPECT scanner to make this CT image. And nowadays, the CTs are pretty good on the front end of these PET CT and SPECT CT scanners And between you and me, I would rather look at the CT from that exam than the nuclear medicine, specifically the SPECT, right? The CT often just gives away the answer like right out of the box, right? We once had this review talk amongst all the fellows and everything in cardiology about why the SPECT scanner got a call wrong. And it was a young woman. She was like 43 or something like that. And the SPECT was normal. And but then afterwards she had an MI, right? And so they called in the SPECT group, say, well, how could this happen? How could, it miss this disease? So the guy came in and he showed the SPECT scan, and then on one slide was the CT for the attenuation and correction. I said, oh, so we'll put up the CT. He throws it up there. There is coronary calcium from start to finish in this woman's arteries. You're looking at it going, that is like 0.005% of humans have that, right? Something's going on here, right? And the SPECT was totally normal, right? And so it was like, yeah, well, so this reconstruction here is just straight up convolution back projection, using the projection slice theorem and then the right filters to do convolution back projection, like that ramp filter. And then, so this is the quote unquote mathematically accurate reconstruction, analytical reconstruction of that data. And the reason it's all bumpy is because of uncertainty in the number of photons that were detected for each view, right? That's just a noisy process. If you had scanned for 40 minutes longer and had way more photons, it would look beautiful. But you don't. So using this as your first estimate, right? And then creating a model of your machine and saying, suppose this is my data, or this is my actual underlying thing, and projecting it through the model and taking the difference between that and the raw data. And what the noise model is in your raw data. So you know what the residual should look like. And you just do that until that error goes down to a minimum. You hit some kind of minimum. And you get this picture, right? And so it smooths out a lot of this stuff that is truly just random noise into a mean. It seems to preserve, a point spread function that looks about like 5 millimeters, right? Something like that. If you're, and then you can just map it back on top of the CT because you have the CT co-registered, which is pretty powerful, right? If you're looking and saying, well, what is this small thing? Where is that? You can map it back on top. And so that's cardiac PET in a nutshell. Here's an example of PET used to visualize in a vessel this inflammatory process. And so this person has a lesion in their carotid artery, and that lesion is inflamed. And what happens is this fluorodeoxyglucose atom is used. So you take a sugar, right, and you replace one of the hydroxyl groups with this fluorine 18 molecule, right? So it looks like a sugar to the cell, but the cell can't metabolize it because it's missing this hydroxyl group. I think I have a picture of it somewhere here. Yeah, here. So this is just a normal sugar, right? And there was a hydroxyl group there, and you put that on there. In your, you've got a half-life of 110 minutes, so you got time to do some chemistry. So you go get that chemistry done, and then you take this stuff, inject it into the patient, and each cell looks at this and says, oh, that's a sugar, and takes it up, right? Now, at that point, the chemistry inside the cell to actually metabolize this thing, it doesn't work because this is here. And so what happens is you just get a picture of how hungry the cells are for a sugar, right? And then it accumulates inside the cell. because it doesn't get metabolized or ejected outright. So those cells that are hypermetabolic because there's inflammation and stuff, they'll show up really bright. Similarly, metastatic tumor, when it's hypermetabolic as well. And so it takes this stuff really fast and lights up. Okay, and so here you get this bright signal in the carotid artery where normally you don't have a bright signal on the contralateral side, obviously here. And it says, okay, there's a lesion there. So this is lower resolution than a coronary, which the coronary vessel is like 2 to 3 millimeters in diameter when it's at its origin, right? And the coronary is moving. This is not moving, right? So you can fix somebody's head and neck and stuff and get just integrate up signal for a long time. Whereas a coronary is moving, it's a much more challenging problem. So if somebody wants to look at that as a project, that'd be cool. What's shown here is, remember, this is the bullseye map. So this is the apex of the heart, the middle from the apex up towards the base. And then this is the base of the heart here. Anterior wall, the patient's chest is up here. Their back is here. Left arm would be over here. This is the left side of the heart. And this is the septum. So this is when you make O15, or remember it had a half-life of like 2 minutes or something. So you really quickly get this O15 water. You usually put it in water. And in some sites, they have like some rapid way of getting that sample over to the scanner and then inject it in the patient. It can be somebody running, or it can be a vacuum tube that goes, and the thing goes down the hall. And then they inject it in the patient, put them in, and then image where the water goes. So water is a very powerful tracer because it can get across the blood-brain barrier like that. There's no barrier to water in any part of your body, essentially. And so it just like goes everywhere. And so when you inject this stuff, you can look at the myocardium and say, okay, where did all the water go in the myocardium? And in this patient, this is a map that is the relative inflow of that water signal for different parts of the heart. So it looks like there's a little, reduction in flow perhaps on the posterior septal wall, something like that. But, mostly the relative amount looks normal. However, the great thing about this technology is that you can, with the signal amplitudes, because you know the injection profile, you can measure it in the aorta or any other input that you're getting. You know what the input is to the muscle. And so you can actually calculate the true milliliters per gram per minute inflow at each point in the heart. So when you make that absolute flow map, this is what it looks like, right? So in the absolute flow map, this person has a terribly low total coronary flow, right? So all of the vessels are involved in this disease. The entire heart is down. And this is not appreciated in SPECT. And unless you do this, absolute perfusion measurement, it's not appreciated in this map either, right? All of the current methods, say in MR and CT and SPECT, mostly use relative flow. So you use the other side of the heart as a control for whether or not the flow is down. And if all of the flow is down, which is what happened with this young woman that we saw, basically all of the flow in her heart was down. So the SPECT was normal. It just had a constant kind of picture. Then you miss this, right? So here's an example of, the activity measured, and this is becquerels, which is like a nuclear activity measurement per milliliter. Excuse me. In the venous circulation and the arterial circulation. right? So these are big vessels. And then this is the counts in the myocardium, right? And so you can model this curve analytically to get what, the inflow is, myocardial blood flow in absolute units, mils per minutes per gram. We already looked at this slide and discussed the nature of this FDG agent. This is an example of the sensitivity of FDG to get picked up in these little tiny spots that, are hot spots for metabolism, and showing that this, this is the patient's liver, right? And so you've got these little hot spots in the liver. So that's not a good sign. Excuse me. So this is a description of a particular condition. And I'll just let you guys read over this. We won't go through it. But where, since we haven't done MR, but where different techniques come into play in order to make a particular diagnosis for something that's it's rare and very specific, right? So one of the advantages of imaging, a lot of the common diseases you can get right just by doing good clinical investigation, good work in terms of asking their history, getting an EKG, doing this, and then you just play Vegas odds, right? And say, okay, the most probable thing you have is this. And the issue with doing that is you can be pretty good just by playing the existing odds of what disease is what. What that misses is all these particular things where imaging can give you a particular signature for something that is not common, right? And so, but it's hard to, as we saw with, doing statistics of clinical trials and everything like that, it's hard to actually prove that you have modified the patient's probability for detecting some particular thing, because you have this background, right, where you get a lot of false negatives because you basically have this huge background that you're just going to be right if you call them negative, right? So anyway, it's the whole issue of diagnostic tests, in particular imaging diagnostic tests, and how they get injected into a pathway of diagnosis, and determining what the value of that added information is not trivial. It's actually pretty hard. And then if you try and calculate the whether or not it's cost effective, I guess would be the best thing to say. Like, is it worth $1,500 to a patient to have this test done, when you look at what the test does to their trajectory through the healthcare system? If you look at cost effective analysis, that whole field, we did it for 4 months or something. We tried to figure out cost effectiveness of coronary calcium scanning. It's a mess. It's basically just a big guess. Just pull on a lever, right? And the reason is that patients go down all these different pathways, and at each node there's a coefficient of, if you have this kind of information and you go that way, or if you have this kind of information, go that way, you can tweak these little node values and get whatever outcome you want. It's a really tough area to work in. So here's an example of using FDG in the heart, okay, or 4 examples actually, where you can look at perfusion and whether or not the perfusion is normal, and then an indication as to whether or not the metabolism is upregulated or inflamed, right? By whether or not the FDG accumulates, right? And the perfusion map here, we say, well, we seem to have some kind of mild defect on this anterior septal side of the heart. And the FDG is accumulating in this tissue, right? As opposed to here where it just went in, came back out, right? This would indicate that you have some kind of upregulated metabolism. And similar here, where we have lower perfusion at this focal level here, we have a very low perfusion here and high metabolism. And then here, you basically have a severe defect in perfusion, right? And this defect on this side. So the stuff didn't get in there at all. So these cells are essentially dead. They're not inflamed and trying to cope with ischemia or hypoxia at this condition. They're just gone, right? So the question is, do you revascularize or try and put blood flow back here? When you look at that tissue, you're like, yeah, I don't know. It's like there's not much left, right? So you're probably not going to recover it. Okay. Okay. What's this? Yeah. Okay. Well, you can read that one. All right. So that's the introduction to PET. What we'll do on Wednesday is we'll start CT physics. I gave you an extra couple of days for problem set 2 because I thought I had pressed the button to announce when it was due, but I hadn't. So that can be due Wednesday, I think I put it to give you some time. But this Friday also problem set 3 will be due. And then if you can send me by Wednesday some partner names. If you want to send a title, that's fine. Or you guys probably want to discuss it before that occurs. And then it'll be great to have an open discussion about the topics and what we're going to learn from your work on the projects. Okay. Any questions? Okay. All right. I'll stick around a bit if there are. And otherwise, I guess I'll see you on Wednesday. Mm-hmm.